Okay, hello, welcome to spectroscopy. We're going to go ahead and continue on with our IR and looking at IR as a way to look for functional groups in particular. As far as what's happening this week, I'll send out a set of spectroscopy homework and IR homework today. And so expect to find that. I'll just send it out as an email so that you guys can have it. It's basically a set of questions from the chapter that I'll be using. What I'll do is I'll give an example of how I'd like you to answer the questions, and then go ahead and assign a set for each of those two chapters, and you'll have a week or so to complete them and upload them back to Canvas. Under the assignments tab, there'll be a homework chapter 1 and a homework chapter 2, and you just have to upload your file to that. If you want to do it in PowerPoint, or you want to do it in ChemDraw, or whatever you want to do, or just want to write it out and scan it, I don't have any issues with however you can get that uploaded to Canvas. I will grade it. Okay. So, and then what I will also do is after a couple of weeks, after it's due, or right after it's due, I will actually give you what I think are the correct answers, and so that you can go back, check, and get some reinforcement that you're doing something right, or you're missing one thing maybe, and we can do a little bit more. Okay. So that's what we'll have today. Let's look at our tentative. I uploaded a tentative lecture and exam schedule. I'm looking for that again. So that should be up on Canvas as well. I don't see it right here for some reason. Oh, there it is. I think it's almost correct. Yes, it should be correct. So our first exam again will be on September 24th. It'll be during class time, and we'll just do it with Zoom proctoring. Basically, what you'll do is you'll kind of put it off to the side. I'll email you the exam. You'll go ahead and use your book, fill in what you can, and then you'll have approximately 10 minutes to scan and upload it to Canvas for grading. Okay, so we'll do that. We'll actually do a practice of that on the week of the 22nd during the review to make sure that both of those things are working for us. Okay. All right. Are there any questions about administration or anything we talked about last time? Okay. So what I'd like to do now is I'd like to continue on with IR, specifically looking at spectra and start figuring out what we can and cannot see in our different spectra. And I'm going to go through a lot of the different functional groups, and I have some interesting analogies or some summations of things like carboxylic acids and how they work, or carbonyls in particular, and how they shift around based on what's around them. And so that's what we're going to do today. And then I have a set at the end where we'll just look at see what information we can find in them and what information we can't find in them. So let me go ahead and share my screen. And there it goes. All right. So I'm sharing my screen, and so this is in the set of slides I sent, which is week 3, part 2. And so with this particular thing, a lot of the spectrum come directly out of the book, but I want to draw attention to, in the book, they do have each different functional group identified as important peaks to talk about, okay? Now, I'm going to stress the ones that tend to be medium or strong in strength. There's some of these that are listed are low in strength and would be supporting evidence of a functional group. However, it's rarely, the identifying peak. What I'm looking for, and I'm going to demonstrate here, is those identifying peaks that make you go, oh, it must be, so that's our first place to look. The other thing I want you to also kind of keep track of is the fact that we are, certain functional groups will show up in certain places. So instead of just trying to look at a number and then look where it is on the chart, get familiar with, oh, you know, hey, there's a carbonyl here. I should start thinking about what types of things have carbonyls. So we have carboxylic acids, we have aldehydes, we have all these things. And so you start looking for other peaks that would support or not support that first guess. Okay, so we want to look for those strong peaks for our first guess and then add additional data as we do to refine it down to, oh, it can't be this, it must be that. Okay, so in this one right here, let me go ahead and get my stylus out here. In this one right here, we have, you know, the first thing we look at is this peak right here. And 1700, very strong, very sharp carbonyl right there. Okay, now what's interesting to note in an IR is as things become more and more symmetrical, the spectra actually gets cleaner and cleaner. So you can actually compare like a symmetrical ketone and an unsymmetrical ketone, and you'll see the symmetrical ketones tend to have sharper, more refined patterns. This is a general rule. It's not a hard and fast rule, but if you start to see things that are getting very clean and you have a very limited number of peaks, you might kind of think symmetry. Now, another way to think in symmetry, especially with rings or carbonyls here, is when you do your hydrogen deficiency index. Okay, remember each one of your hydrogen deficiency indexes can be a double bond or a ring. So you want to keep that in mind when after you've calculated that. So in this one here, we have, of course, no hydrogens above the 3000 mark. So we have no aromatic rings. We have these two sets right here. And we don't have a peak at 2700. So we probably don't have an aldehyde. So we have some kind of carbonyl compound that has only aliphatic peaks. And in this case, we're looking at this symmetrical ketone where probably these hydrogens are the ones that are slightly down here and the rest of these hydrogens are the ones up here. Okay. And then we have our little fingerprint region is actually very minimal as well. So again, with this, the functional group here is the ketone, and we're looking at where this carbonyl is. Now, remember, that carbonyl shifts up and down depending on what's bonded to it, and I have a different slide for that. Okay. So as we move to a very branched hydrocarbon, what we're going to see is that these peaks that are in below 3000 here, notice we have multiple numbers of them because we have multiple kinds of hydrogens that are those hydrogens bonded to sp3 hybridized carbons. So we have these primary hydrogens for here, we have a tertiary hydrogen, we have a secondary hydrogens. And so because we have all these different types of hydrogens, we're going to get these multiple peaks and they're going to overlap each other. But again, they're all under 3000 and there's no peak at 2700 and there's no carbonyl. So we're probably not, we know we don't have any hydrocarbon. Notice there's also no carbon-carbon double bond peaks, no carbon-carbon triple bond peaks, no alkynyl peaks. So we now think that, okay, this is a really good indication we have a fully saturated hydrocarbon. Okay. So that was a fully saturated hydrocarbon. We had no carbon-carbon double bonds, okay? So now, by the introduction of just two sp2 hybridized carbons with hydrogens on it, we get two new peaks, okay? Going just from comparing what we had before, we get those two new peaks. We get the carbon-hydrogen peak here. So this is that peak. And we get this carbon-carbon double bond peak, okay? So if we had that previous compound and we heated it with acid and it looks like we generated a peak here and a peak here, it means we've functionalized that, or we changed the compound we had. And so it's just these two little peaks. They're small, but they're in the exact right place for our carbon-carbon hydrogen bond and our carbon-carbon double bond here. Questions on that? Okay. So moving on from there, By taking that carbon-carbon double bond and adding another one to it, we actually start gaining strength in that bond, that carbon-carbon double bond. But we've added another bond here. We've added another peak here. So we have our aliphatics that are below. Those are the sp3 hybridized hydrogens. We have our peak growing at stronger now because we have more of those double bonds, right? We have 2 double bonds now. And so that peak's growing in. And then we also have our 1600 peak. That's our carbon-carbon double bond. But we have this new peak right here, the 1794, okay? So if we go to our book, oh wow, the book doesn't show, there it is, okay. If we go to our book, what's in that range? That looks different than anything we've had before. So what could that mean? Okay, and if we look at our alkenes right there, we see that we get a peak. Where is it? It's not there. As we start to conjugate these alkenes, we get this new peak coming in. And that new peak is assigned to the idea that we have a conjugated double bond system. Okay. It's not the peak's not in my table. Okay. So in your book, in the section 2.6.4.1, there's a thing called conjugated systems. And when you have a conjugated double bond, you not only get that, but it's not listed there. That's interesting. In my other book, this peak right here indicated we had a conjugated double bond, basically a double bond, single bond, double bond. Our book does not say that, so, oh well. Okay, so we have our strong carbon-carbon double bond, and we have hydrogens above and below the 3000 mark. Okay, so let's go from that conjugated system to our alkyne. And again, we have all the same peaks that our hydrocarbon would have with our peaks below the 3000 here, but we have now our alkynyl hydrogen, which is higher. It's the 32 to 3300, and we have the carbon-carbon triple bond. And again, there's only 3 things that happen in this region, and so when we see a peak there, we need to pay attention to that as a carbon-carbon triple bond. And then we double check with our hydrogen deficiency index to make sure we have at least 2 in our hydrogen deficiency index so that we can support the idea we have that double bond. Now, if we can't do that with our hydrogen deficiency index, can we find a nitrogen in our system somewhere? And maybe it's a nitrile at that point. Okay, so as we move on to the aromatic systems here, remember with the aromatic system, we have, again, a carbon-carbon double bond, and that gives us this 1600 right here. And what we'll see here is if we only have aromatic hydrogens here, we're only going to have peaks above 3000. But the fact that we have these 2 alkyl substituents means we have them above and below 3000. And notice, other than that, there's almost nothing happening until we get to this 1500 range here. So it's a very nice clean peak. And again, this is a symmetrical molecule. All right, so now I want to talk about sometimes all of these compounds up to now have been neat liquids, meaning they just put a drop of it on the IR and you're measuring it there. Now, when you have neat liquids like this, you are getting everything about their natural state, and you're getting very strong peaks because you're going through the entire sample is allowed to absorb the IR. Now, when you have something like an alcohol, okay, you occasionally want to see if there are peaks underneath that big OH peak, okay? That big OH peak has everything to do with hydrogen bonding, okay? So the more concentrated your solution is, the more likely it is to hydrogen bond. But by taking your alcohol and preparing it in a solution that does not hydrogen bond, you can actually narrow that big wide OH peak and look for a free, clear OH peak by itself. Now, the way we can do that is we can actually dissolve up our alcohol in a solvent. And in this case, we're taking an alcohol and we're dissolving it up in carbon tetrachloride. Now, carbon tetrachloride is used as an IR solvent a lot because it only has absorbances down below 1400. Okay, the carbon chlorine bond actually absorbs way down in the 700 range. And so you have this very clear place to see a lot of the other functional bands. Okay, so at a very, very low concentration, and if you look at here, it's 0.3 molar solution here, we actually can break up almost all the hydrogen bonding that we have, and we actually get to see the free OH peak. This is the OH peak. That's the OH vibrational frequency in the absence of hydrogen bonding. And it's about these are in microns, so this is 3,300 wave numbers. I'm calculating that right. Okay, but notice how it's nice and clean, and that has everything to do with hydrogen bonding. Just by increasing the molarity, the concentration to about 1 molar, we still can see that free peak, but we get this huge, broader peak. That's that hydrogen bonding. Okay, so I talked about how the big broad peak is there for hydrogen bonding, but you can actually prove that by doing these dilute solutions in a non-hydrogen bonding solvent. And I want to draw your attention to that.
I have a question.
Yes.
Yes, this by dissolving them in the solvent, you will decreasing the intermolecular hydrogen bonding or intramolecular?
Intramolecular. Oh yeah, it's spelled wrong. Sorry. It's because the separate molecules of the alcohol are hydrogen bonding to each other, and that gives us the broad peak. By separating them out and diluting them so they can't interact with each other, we break up that intramolecular, between the different molecules, not within the molecule. Yeah, so it is, intermolecular is right.
It means if there is a hydrogen bonding within the molecule, so it will be a little bit broader than the...
Correct. And actually, that's an interesting point, is if you have two alcohols on the same one, this will not always break that up because it's within the molecule itself. Yes. I don't have an example of that, unfortunately. Okay, so let's look at some other alcohols here. So the alcohol actually can shift a little bit based on what kind of electronic structure it's nearby. In this case here, we have a phenol. We have the OH group on a benzene ring. And so we still see the strong hydrogen bonding. We see that it's shifted down ever so slightly. It's usually centered a little bit more here. It's starting to get closer to where we'd see that the OH on a carboxylic acid overlap down here. It shifted slightly down, and the rest of the peaks where we should see are here. All of the carbon-carbon double bonds show up down here in that 1600 range. And again, if you were to dilute this up in a non-hydrogen bonding solvent, you would see that peak diminish. And these peaks in this range here would start to become more pronounced and easier to see. Okay, so if we actually take this phenol and functionalize it to get rid of that acidic proton by turning it into anisole, or this methyl ether derivative here, we completely lose that entire set of hydrogen bonding. That's all gone because we don't have the acidic proton anymore. And we have all of our little peaks here. Now notice the peaks above here are from the benzene ring, the peaks below are from the methyl group here. But then the only other peak we have is our 1600 peak right here, which is our carbon-carbon double bond. And then we have our fingerprint region down below. Okay, so this is another example of a functional group transformation. If you had phenol and you reacted it to form an ether using an ether synthesis, you would expect that OH to disappear and be able to see those new peaks from that aliphatic addition. Okay, so now let's look at a different kind of alcohol. So here, instead of being phenol, we have separated the OH from the benzene ring by this benzyl group here to give us benzyl alcohol. Okay, so notice that the peak is now not as broad right here. It's been separated from where the phenol was, and we actually get to see the benzene hydrogen peaks and these benzylic hydrogen peaks here. And our 1600 peak has actually diminished a little bit from that. So the OH is the dominant feature in this system. But notice it has shifted from where the phenol was, okay? It shifted up higher, it's about 3330, where the phenol was shifted slightly down at this 3250. So there has been a shift because of the way in which those two different alcohols can hydrogen bond. Okay, so let's go to a purely aliphatic alcohol, and we'll see we have that almost that same position, the 3330, for that aliphatic alcohol. But again, we've lost all of our aromatic hydrogens. We only have our aliphatic hydrogens. And notice we've lost that, that C double bond C thing at 1600. So it's another example of, you know, the electronic condition here being bonded to that sp2 carbon will shift this slightly, and we'll look for the peaks that support our theory. Now, I bet our hydrogen deficiency index on this compound should be 0, so that we wouldn't even want to look for aromatic rings too. All right, questions?
On the last graph we looked at, the peak for the benzene ring at 1600, why was it smaller than in the previous examples?
I don't know. I don't know. The strength varies depending on electronic structure. The strength varies also on how you prep the sample. That's why it's not really labeled, is that we expect it to be there, but it's smaller than what we would consider a medium peak, so that's why it's not labeled. But we do see it, it's just not it's not in our medium to strong peak range. Did that answer your question? Okay. All right. So now let's go start it into the ketones and look at how the ketones have some. And this is, of course, acetone, one of our more common ketones. And one of the things we will see here a lot in samples is if they're hygroscopic, we'll start to see water dissolving in our system. And so this band up here is actually a little bit of water dissolved in our acetone. Okay, so acetone likes to form a hydrate, and so there's always about 1% of that hydrated acetone in the system, and that's what this little broad peak here is. So we see that frequently unless you have really, really dry acetone. But the rest of the structure is easily identified by its functional components. We have our sp3 hydrogens, and our carbonyl compound right here. Carbonyls are always strong. In fact, I've never seen a medium carbonyl compound. I think they're always strong. So we have a nice way to recognize them. Now, once we see this carbonyl, we also want to start looking for other peaks. Is there an OH peak for a carboxylic acid? Is there an aldehyde peak? And if in the absence of those two things, we start to see, okay, it's got to be an ester or it's got to be a ketone. Okay. But how can we kind of hone in on this a little bit more to tell us what should I think about first? And actually, it turns out that that carbonyl peak changes because of the electronic conditions around it. So as you change the groups attached to that carbonyl, you'll actually see that carbonyl shift. And so what we can do is start to say, oh, it might be this because it's shifted higher or lower in the band, okay? And that table is the next one here. Okay. I actually stole this from a different book. It's not in our book. So, but it gives you a really cool idea about where to look for these carbonyl frequencies by functional group. Okay. So the highest frequency available to us in the carbonyl range is actually this 1815 to 1790 wave numbers range. Okay. So it's this really high number here. And this has to do with the fact that we have a chlorine, a very electronegative atom, is pulling electron density away from the carbonyl. If it's pulling electron density away from that carbonyl, it's making it vibrate at a higher frequency because it's changed the strength of that bond. Okay, so it's shrinking that bond, making it vibrate at a higher frequency. Okay, so we can do that another way is to do that where we attach an ester nearby. Okay, so we've added this ester here, not a carboxylic acid, just the ester. And the reason we have an available to us is by resonance, we can generate this partially negative charge on oxygen and this partially positive charge on the other oxygen by resonance. When it does this, it again shrinks that bond slightly and gives it a slightly higher frequency than an aldehyde or a ketone. And so we'll see that in the 1750 to 1735. Notice that this is just a resonance effect and not a direct induction effect. The chlorine here is 100% inductively pulling electron density away, therefore the shift is greater than in the case of this ester. Okay. Now, let's take away that electron withdrawing a minute and add a hydrogen for an aldehyde. Okay. We'll still want to look for our 2700 peak, but the idea is hydrogen and carbon have about the same electronegativity, so that's not a really polarized bond, but the other carbon can slightly donate inductively to give us a little bit of polarization in this bond, and we get it a little bit higher than our 1700 to the 1740 to 1725. Once we take away that hydrogen, we've dropped it again to the 1720 to 1710 area there. And that's exactly where it was in acetone. Okay. Now, one of the other functional carboxylic acid functionalities here, we had esters, acid chlorides, those are carboxylic acid functional groups here. When we go to the amide here, the amide is not as electronegative as oxygen. Okay. So that polarization is not as strong, but the nitrogen can more easily stabilize the positive charge. And we actually end up weakening that bond. It's less strong than it was as the carbonyl, and the number drops below 1700. Okay. Now, once we take our carboxylic acid and deprotonate it and let it completely act for resonance, in resonance in this lowest one here, right here as a salt right here. Now think about that. That means only the bond is not near as strong because it's being shared over two different atoms. We only have a partially double bond on one carbon and a partial double bond on the other carbon. Therefore, it shifts it all the way down to the 1600 to 1650 range. Okay. But then there's also another peak here that we usually don't see. It's usually in the fingerprint region. It's there. But if we have a carbonyl that's shifted almost as low as a double bond, we start looking for that carboxylate ion. Okay, so what I really love about this chart is you can look at the electronics, that changing electronics of that carbonyl, and watch it shift from high frequency to low frequency. Okay, does that make sense? Okay. And I only added this last year because I found this really cool chart in another book. Okay, so let's go back and look at the carbonyl here again. So this right here is our ketone. That's the middle of the road carbonyl. It only has those carbons that have the same electron electronegativity as the carbon on the carbonyl. And so we have a nice strong peak right in the middle of our zone, 17, 15. Okay. Now, having something like a benzene ring next to it shifts it down. Why? The benzene ring is electron rich. It's electron rich, so it's going to donate electron density, letting this bond get a little bit longer, and it shifts it down just below 1700. Okay. So if it's electron withdrawing, frequency goes up. Electron donating, frequency goes down. All right. So let's look at some other carboxylic acid, and we're going to go in order from top to bottom. If we look at this acid chloride right here, notice we have a chlorine right here. We're expecting that to be at the high end of the frequency. And what we see is we get it's 1780 and 1750 here. And so those are, that is the peak for the carbonyl itself right here. We have aliphatic and aromatic hydrogens. So we see the aromatic hydrogens and the aliphatic hydrogens, okay? But we still have our 1600, which is our carbon-carbon double bond. So the other thing to note, is that carbonyl is still very strong, but it shifted way higher than it was in acetone. Remember, acetone was like 1750. It's really high. Okay, so part of that, I mean, that has the direct involvement of that chlorine withdrawing. And probably a little bit of the idea that it's shifted a little higher than even we were thinking, because we have donation from the benzene withdrawing from the chlorine. And so that's probably has some resonance effect that shifts it even higher. Okay, so moving on from acid chlorides to the next one, an acid anhydride, okay? The acid anhydride is fairly similar to the acid chloride in the fact that we're looking at this oxygen is not as donating because it can donate to these two sides. So it doesn't donate like an ester. In fact, it looks a lot like a acid chloride here. We only have aromatic rings here, and we have our carbon-carbon double bond. And yeah, I'm not sure. I don't know what that 1717 is. I'll have to look that one up. Okay, so moving on from that, we had acid chloride, acid anhydride, moving it down to the ester. Here, this is actually a fairly electron-rich ester because we have donation from the aromatic ring, but we have donation from there. So we get our shift at 1771. Remember, our ketones are lower, and our things with those esters like this are higher. They're just below that acid chloride in the 1770 to 1750 range. So we can watch it shift again by taking it to the aldehyde. And now it's shifted down closer to 1730 right here. And notice we have our peak at 1700, which is this hydrogen on the carbonyl. Questions on that? Do we see how these peaks are shifting and why they're shifting? That's the important part here.
When you have something that is going to be electron donating and it's also in the presence of something that's electronegative, so it'll be electron withdrawing, do they kind of work together to shift in the same direction instead of working against one another? Whereas if you had something like the benzene ring without another electronegative atom, it would just be withdrawing?
Yes and no. Okay, what I mean by that is there's this direct inductive effect with the electron withdrawing. And with the electron donator, you have to start drawing the resonance structures to see where the charge ends up, okay? So if you end up with a negative charge in a resonance structure trying to be on your carbon instead of the oxygen, it's not going to be a contributor. It's not going to lower the bond energy. So it's not a hard and fast rule, but I think the hard and fast rule is if it's a directly connected and a direct withdrawer, like a halogen, then you will see that effect. With the oxygen or the benzene ring, it might be less of an effect based on resonance contributors. Okay, so in those conditions what we actually saw that was a resonance contributor where we had separated charge. That's a minor resonance contributor. The neutral one, it would be a major resonance contributor. Does that make sense?
Yes.
Okay. And the more resonance contributors you have, the more likely you'll have, a broader peak, a shifted peak, because you're getting the net sum of all of those resonance contributors. Okay, moving from the aldehyde to the carboxylic acid, the first thing we note is the big peak overlapping our 3000 band here. This is the OH, of course, and our carbonyl here is shifted down toward the lower end. It's down in the 1700. And if we deprotonated this, it would shift down even further. Right here. And so probably these are the hydrogen peaks here, and this is just maybe some dimerization peaks. But this big overload peak is the OH on the end here. Okay, so moving from that carboxylic acid to the amide, we actually have two features I want to show you here. This is the first time we've shown an amine at all, or a nitrogen containing hydrogens first. And we also have something else. We have a carbonyl, and that carbonyl is in conjugation with a double bond. Okay, so now we have this complex set of things happening, but I want to elucidate each of them independently. The first thing is the carbonyl here is next to this electron donator and an electron donor, which is shifting our peak down here. Okay, because it's in conjugation, we have resonance contributors, meaning we have two peaks in this carbonyl range. Okay, so that's telling us something. So the first peak here is going to be our carbonyl by itself. The second one is going to be our carbon-carbon double bond. But it's shifted a little high from that 1600 because it's in conjugation with the carbonyl. Okay. So the next thing we need to look at is that we have this hydrogen with the nitrogen with two hydrogens on it. Okay. Now, nitrogen can hydrogen bond, and therefore we get the broad peak right here. Okay. The other thing is, because of those hydrogens, the actual electronic configuration around nitrogen is tetrahedral, meaning that those two hydrogens are fixed in space, okay? And they're not equivalent. And therefore, whenever you have two hydrogens in a compound on nitrogen, you get two peaks in this band. If we take one of those hydrogens off, one of those peaks goes away, and some of the hydrogen bonding goes away. We take both of those peaks, both of these hydrogens off and replace them with carbons, peak goes away completely. Okay, so the three things to look at on this one is, we have our carbonyl peak shifted down because of the amine. We have our carbon-carbon double bonds shifted slightly up because of conjugation. We have our hydrogen bonding in our amine, and we know we have two hydrogens on the nitrogen because we have two peaks. I think I have an example of removing one of the hydrogen. No, I don't. So if we were to take this compound and turn it into something like this, where we replace one of them with a methyl group, what we'll see is we'll get one peak in that range, and then of course the aliphatic stuff in the carbonyl down here. And then if we replaced the other one, that peak would go completely away. We just have our aliphatics and we just have our carbonyl. So it gets cleaner and cleaner as you get rid of those hydrogens. Okay, so let's talk about amines by themselves. So this is an amide because we have that carbonyl on there. We have 2 hydrogens possible. Let's go on to amines themselves. So this amine right here, actually we have 2 different amines, one's at each end. However, that's not why there's 2 peaks here. These 2 peaks here are here because we have 2 hydrogens on that nitrogen. Notice the peak is slightly broad because of hydrogen bonding. And all of these are our aliphatics. And we have something at 1600, which is our carbon-nitrogen bond. Okay. Actually, is that right? No, that can't be right. A carbon-nitrogen double bond. 16. It's not supposed to be here. I don't know what that's 1700. Oh, yeah, aliphatic primary amines have a medium peak at 1600 as the carbon-nitrogen bond. Good. Thought I forgot. All right. So moving on to other nitrogen compounds, we have now our carbon-nitrogen triple bond, right? And so that's the nitrile functionality. And remember, there's only 2 things in this band, well, technically 3. There's 3 things in this band, and it's the carbon triple bond and the carbon-nitrogen triple bond nitrile. And so notice it's a nice clean peak. It's rarely more than medium, but it's usually very sharp and very easy to see. We have aliphatic and aromatic hydrocarbons here, and these are for our benzene ring right here, and then everything else is below 1500. So the other thing, I think I have it. Nope. Okay. So the nitro group actually is not IR active very much. It's got a very low, because of the heaviness of the atoms, they're in this region here. So whenever you have a nitro compound on here, you're probably only going to ever see the aliphatics. And notice everything else is way down below. This, the 1600 and this number here are for the benzene ring, the carbon-carbon double bond. And everything else is pretty clean in that area. This should be the thiol. Yes. The only other thing that shows up in that 2500 to 2000 range is the thiol, okay? And the thing I want to talk about this is that, okay, if our OH is up here and our NH is here and our CH is here to here, depending on whether it's triple bond, double bond, or single bond here. We now have our sulfur hydrogen here. And we see this shift of this heavy atom to light atom going there, mostly because this is a more polar bond. This has a more polar bond because oxygen is more electronegative than nitrogen. And therefore, that is a more polar oxygen-hydrogen bond than the nitrogen-hydrogen bond. Okay. Now, the carbon-hydrogen bond is even less polar, and it's only the acetylene hydrogen bond is more polar than the vinyl hydrogen bond, which is more polar than the carbon hydrogen bond. And likewise, the electronegativity difference between sulfur and hydrogen is actually less than the electronegativity difference of carbon and hydrogen, or approximately the same, which is why this is the only hydrogen that'll show up way down here. Our only other one is the aldehyde peak, which shows up at 2700 here. Okay. So I thought it was really interesting when I was doing some research on this that polarization of the atom-hydrogen bond gives you that shift in frequency. The more polar the bond, the lower the frequency. I'm sorry, the more polar the bond, the higher the frequency. The less polar the bond, the lower the frequency. Okay. All right, and let's do one last thing. As we take our benzene ring and we substitute it with other atoms, for example, in this case of we're replacing a CH with nitrogen to give us a pyridine ring, what we see is we just get a slight change in that position of that carbon double bond. Our our hydrogens don't move very much. We have a slight shift downward from 1600 to 1580, and that has to do with the electronegativity of nitrogen in the way it aromatizes the ring. Remember that aromatic ring is not exactly the same because we have the electrons from the nitrogen contributing to the aromaticity, and then we also have a lone pair sticking out here that contributes to spacicity, and that combination of being not the same electronic structure as carbon shifts that peak down slightly. We see that in other hydrocarbons as well. I'm sorry, heterocycles as well. All right, so.
I have a question.
Yes.
So the lone pair of the nitrogen is like creating more delocalization. That's why it's moving down?
No. One lone pair of the nitrogen is delocalized into the ring to make it aromatic. The other pair of, because the nitrogen is sp2 hybridized, the other pair is just sticking out. So the benzene pi clouds are above and below, and it's sticking out perpendicular. So it doesn't have the same amount, and it's more electronegative than carbon. So that changes the net aromaticity of the system. So now what I want to do is I want to go ahead and start with 3 spectrum, and then we can open our mics up and start theorizing what might be in which spectrum, and maybe we'll figure it out, or maybe we'll just get some supporting evidence. So the next thing I want to do is I want to just pull up this spectrum here. And what can we see here? Do we have any alcohols?
No.
No. We don't have any amines. We don't have any nitriles. We don't have any acetylene. I don't even think we have a carbon-carbon double bond in this thing.
We have a carbonyl.
Ooh, we have a carbonyl. And what kind of carbonyl would it be just from that number? Is it going to be an acid chloride or an ester?
Acetone.
Acetone?
Sorry, ketone.
So I agree with you 100% that that's probably something that is probably something like a ketone. It's completely aliphatic, and there's no other functional group present. So it's probably a simple symmetrical or a simple hydrocarbon-based ketone. Can we get any other information from this? Probably not about functional group, because really there's some peaks down here, but they're below the 1500. If we had a computer, we could try to match it, and we can actually get purity based on these little peaks here, but we don't have that. Okay, so let's move on to the second one here. All right, what do we see?
Broad P hydrogen bonding.
Right, okay. Is it nitrogen or oxygen or sulfur? We can get 2 things from that. We get shape and position, peak, on whether or not it's a carboxylic acid, OH, an alcohol, an amine, or a thiol, right? So right away, is it a thiol?
No.
No, because that would be,
No.
right? Okay. So if it was a nitrogen with two
Two
hydrogens,
peaks.
it would
There
have
are two hydrogen, two peaks.
and it would be slightly shifted down. The nitrogen peaks are a little bit lower, around 3,000 or 3,200. So that's, because this is up at 33, I'm going to say that's an OH peak right there, bonded to a carbon. Okay. What else do we see in our spectrum? All of the protons here are aliphatic. We have no functional groups. We have no carbon-carbon double bonds, no carbon-carbon triple bonds. I don't think we even, I think that's all we can tell on this one right here. So given a molecular structure or a molecular weight, we could probably get a pretty close approximation. Okay, all right, so how confident are you that we can definitely assign the major functional groups just by doing our first glance at our IR?
Pretty confident.
Pretty confident? Because what's helpful is during the exam, I'm going to give you sets of information, right? So on our first exam, I'm going to be giving you a mass spectrum and an IR, okay? So can you 100% assign a perfect structure to that? Probably not. But if you draw a structure that is supported by every piece of information you have, then that's going to be, you know, 90% of the points, okay? So by being able to quickly recognize major functional groups, it'll get you started down the path of, okay, how does this fit into the data I have from mass spec? For example, if you have this big peak here, do I see a loss of 18 in my mass spec? Because if I see a loss of 18, then I know that that fragment that was minus 18, that might be the major fragment of the rest of my molecule. And I can start to assign the mass of that fragment. Okay, so in this one right here, we can predict just on spectrum B here that our mass spec will probably not have a 77 or a 91, because the 77 is benzene and a 91 is a benzene with a carbon in the benzoic position. So we can start eliminating things from our possibilities, okay? So this is how I want you to kind of approach these things. Okay, I have a little evidence here. I got this, this, and this. I get a little evidence from the mass spec. Okay, now how can I refine it? Does this support this? Does this support this? And go back and forth, back and forth, back and forth. And then when we add NMR, mass spec is going to tell us a lot about the atoms we have. The IR is going to tell us a lot about the functional groups we have. The NMR is going to tell us how that's all connected. And we'll know exactly how many hydrogens are next to other hydrogens. And we'll know the connectivity of, ooh, I have two hydrogens next to something that electron donates because of where it's shifted. Okay. So we're adding evidence to evidence to evidence to give us a nice, firm idea of what we have. Okay? So that brings us to our last one here. Boy, that one looks a little weird. I don't remember what this 1890 peak might be, but it's labeled, so it might be important. So is it a purely aliphatic compound, or?
No.
Probably not. We've got some peaks above 3,000, and they're not very strong. We got a nice peak at 1,500. So that's a little low for a carbon-carbon double bond peak. But what's that 1890 peak? I don't know. Let's go to our little book here and say, you know, there's going to be probably 15 different things that can be 1890, but we can eliminate a lot of those by what we see. Okay. So let's look at that.
It's a carbonyl conjugation with double bond?
Most carbonyls are very strong.
Okay.
I would consider that a weak peak. So, so it's probably not a carbonyl. Let's see, what else would be in that range there? 1890. So it can't be an ester because that's not in the right place. Can't be an alkene. It could technically be a monosubstituted benzene if it had a weak peak in that range. That might be what we see. What else is in that range? Almost nothing is in that range. Can't be a lactone, can't be an amine, can't be a nitrile, can't be a CO3. So, being that we only have one thing that's possibly plausible, is that benzene has the opportunity to have a weak peak in this band. And we have both aromatic and aliphatic, so it might be some kind of benzene peak. And we might have some kind of substitution on it that has something like maybe a nitro or something. But that's all we can tell from this, right? Now, if we were given a mass spec that tells us we have one nitrogen in there and a couple oxygens, we might be able to infer that we have a different functional group. Okay, so now we'll have to go to whatever evidence we have beside this to help guide us. But we're not looking for ketones, we're not looking for aldehydes, we're not looking for esters. We're looking for some kind of monosubstituted or disubstituted benzene. Okay, so do you see how I would want you to look at each of these spectrum and look for the major functional group first? And then have that guide you to go to the next step on solving the puzzle. Okay. All right, let's do 3 more real quick just to kind of give us an idea. This one right here, it's obviously benzonitrile. No, I'm kidding. What do we see?
Aliphatic hydrogen.
Alkane.
Yeah, aliphatic hydrogens and nothing else. So it's probably a straight chain hydrocarbon of some kind.
Aliphatic alkane.
The reason I say that is because you have more than one kind of.
CH2.
So you probably have a branched hydrocarbon, so you'll have primary, secondary, and tertiary hydrogens. So that's the one piece of evidence we can get from this. Okay. All right, make it a little more interesting. All right, no carbon.
Another carbonyl.
Yes, we have a carbonyl, and based on its position, it's probably
Ketone?
Probably a ketone, because it's right at that low end of the idea. We don't have a 1700, a 2700 here, so we probably have some kind of hydrocarbon and a ketone. All right, this one should be screaming one functional group to you.
Amide.
Amide, interesting. The nitrogen peak should be at the 3200. Remember, it's 3300 for oxygen, 3200 for that.
Okay.
The peak.
Carboxylic.
Exactly right. Carboxylic acid. So carboxylic acid, I'm not sure we can trust that peak above there. So let's see if there is a carbon-carbon double bond that would support having a benzene ring, okay? If we look back over here, we don't see anything in the 1600 range. So this little peak might not be, I would say this is not a aromatic carboxylic acid, but it is a carboxylic acid because of this peak, and it's probably aliphatic because of this peak. Now, based on the shape of this peak right here. Is it an ester? Or not the shape of the peak, the position of that peak?
No, it shouldn't be ester, I think so.
No, it's not high enough.
Right. So the ester would be over here.
Yes.
An acid chloride would be over here, but we have an OH here, so we can't. And it's not a carboxylic acid salt because it would be shifted down that way. So we just have a free carboxylic acid, probably neat to allow it to hydrogen bond and give us that spectrum. And we have no double bonds, and I don't see anything big other functional groups there. So, okay, so are you getting more confident about identifying like at least the major functional groups? Okay. Now, in our, let's see, when is our next activity? Our next activity is on the 15th, which is next week. On the 15th, I'm going to do a set of problems in class where we have IR and mass spec. And we're going to go analyze the mass spec, analyze the IR, and go back and forth, back and forth, back and forth until we have a reasonable assignment, okay? And that is going to be, then we'll have an activity on Thursday that's the exact same thing. I'll review anything I might have missed, and then we'll have our first exam on the 24th of September. Okay, good. I finished a little early today, but I think that is a great place to stop. And so when we come back on Tuesday, I will pre-email you a set of mass spec and IR. I want to do about 10. We're going to go through 10 of them in class and do that whole thought process again. We're going to be calculating, you know, using the rule of 13, using substitution, using the 1.1 isotope for figuring out the number of carbons. And then we'll look at our IR and look for which functional groups, or we'll be able to say, hey, look, there's probably a nitrogen in there because of this. But it's an even peak in mass spec. Oh, there must be 2 nitrogens. And so we'll be able to go back and forth, back and forth, back and forth and support our theory, okay? Any questions about functional groups in IR? Again, in your research, if you do these functional groups right here, there's a lot of little subtle details of overtones and stuff like that, and you can see if things are dimerizing or not. It's in the book, but I don't want to bore you with details that might not apply to your research, but you can add those additional things from the book into your research at any time. Well, that's all I have. If you have something else to do, go ahead and head on out, and I'll stay here and answer questions if you have them. I'm going to stop sharing. Oh, I should stop recording too. There we go. I'll just post